we should move on to the next part, which is a lecture by Professor Janani. Once we are done with that lecture, we will go through with the next tutorial before we break for lunch. So I know Professor Janani has been speaking to all of you, addressing all your questions, everything since yesterday. She did give us a short talk on CFD as well yesterday. But to reintroduce Professor Janani, she is an assistant professor of the Mechanical Engineering Department at IIT Bombay here. And she completed a PhD in mechanical engineering from IIT Madras, post which she has been at Iowa State University and also a researcher in the mechanical engineering department at Imperial College London. Um, at IIT Bombay, she specializes in the areas of computational fluid dynamics and multi-phase flow and heat transfer. She has a lab that she runs with the same name, multi-phase flow and heat transfer, and also works on biofluid dynamics. Her current research interests are in the areas of boiling and bubble contact line dynamics, which includes blood flow modeling as well. So with that, I request Professor Janani to please address the participants and give a short talk on laminar and turbulent flow. I'm sure that is very well in line with all the tutorials that you have been working on. We will get to the turbulent part of the tutorials later during the day as time permits.
Thank you, Shweta. Hi. So I think this is the second part of your workshop day, as well as the second phase of the workshop. You would have finished most of your meshing related work. And now you're slowly moving on to a slightly bit more application oriented problems. So there is a reason why in spoken tutorials for OpenFOAM we picked the standard flow through a pipe, laminar and turbulent flow problems, because these can very easily be extended to more complex cases, number one. Number two, it gives you a ready-made framework to understand some of these fundamental physics-based, how are you going to monitor some of these values? Does it adhere to the physics that's expected? Does it give you a parabolic profile, velocity profile? So it's pretty easy to compare and verify against analytical solutions. And a lot of important CFD-related problem setting issues, queries that you would face in a more complex geometry gets addressed here as well. So I think it's a good mix of things. So my talk will not give you a rework of what the fluid mechanics of flow through a pipe is. That's not the intention. But to have and assume that you have that baseline understanding, but to jump off that and see what critical CFD-based decisions need to be made to simulate. Okay. So the bottom line for any kind of flow is that the flow happens in relation to some stationary boundary, right? You can call it by the standard nomenclature of quote unquote external flow, wherein there is a boundary layer development. So I presume all of you know what I mean by boundary layer. So there's this stationary wall or a domain boundary. And because flow happens in relation to that, there is going to be a certain boundary layer that's developed. And the boundary layer typically is our construct of a physical phenomenon. So what is our construct of a physical phenomenon? There is a variation in the velocity profile, right? So the variation in the velocity profile is what we construct as the boundary layer. So in an external flow, there is no other boundary which is affecting the formation of one boundary layer. Now, when you talk about quote unquote internal flows, then you see an enclosed flow wherein the boundaries of this enclosure, in a way, modify and affect your boundary layer development. Okay, so typically you would see two categories, which is external flow and internal flows, and this is basic fluid dynamics. Now, what is important for a CFD professional is an understanding of whether they are dealing with a velocity profile which is quote unquote developing, or it is a velocity profile which is already developed, because the treatment is slightly different for both. What do I mean by this construct or this terminology that I've used, right? So if you do have, say, flow through a pipe, which is what we're going to look at, and typically at the inlet of the pipe, you do have a uniform profile of velocity that's going to be entering, right? Now, as you move along the tube, at the walls, you're going to have a no-slip boundary condition, which means that there is no velocity if your boundary is stationary. So the layer of fluid right next to the next to the boundary condition is going to remain stationary. So there is some velocity profile that's developing, right? But it is only the layer right next to the wall which has realized there is a wall, and the information has not propagated yet to the entire pipe. So this boundary layer is going to keep growing till the information propagates towards the entire medium. So there is definitely a region where the velocity profile near the wall constantly changes. Okay, and this is known as the entrance length. Once this change has completed and the entire domain is aware that there is a boundary layer, the velocity profile ceases to change after a point. And that's called the fully developed region. And what is the characteristic of a fully developed region? The velocity profile does not change anymore. Okay. So for a CFD person, right, this becomes a very critical point for two reasons. We will just take a step back from that point. Keep in mind that point. We will come back to that, right? So when you're solving a problem as an engineer, or even for research problems, typically just simulating a flow through a pipe doesn't get you anywhere. There are certain information that you want to derive from it, okay, which we, or I would like to call, engineering parameters, okay? Why? Because you're going to use this information to design certain systems, maybe pipelines. So what are the engineering parameters? Number one is the standard velocity. Is my fluid coming out with a velocity that I would like, with a force that I would like? The second related question is, what is the kind of pump power that I would need to provide to be able to achieve a particular velocity? Okay. And by pump power, we only mean that power enough to overcome the pressure drop between the outlet and the inlet. Okay. So this pressure drop needs to be provided in order for flow to happen. So why does the pressure drop happen? Let's just understand that a little bit. There's flow that's entering, and there's going to be friction at the wall, maybe a few other head losses because of pipe turning in and out. And hence there is a balance which has to be reached. You're going to lose energy to friction. So there is a standard pressure drop. Now, if flow has to happen in and over this, then pump has to be able to cause a thrust to overcome this. Okay. So the entire process, as you can see, a large part of the contribution is this very much interaction with the wall. Okay. And a related term with the friction is your wall shear stress. Okay. So based on the critical requirements as an engineer to ensure a particular velocity flow and to understand what kind of power is required, one needs to understand that, you need to know what is the pressure drop that's happening from the pipe, what is the wall shear that's being experienced locally at the wall, and the velocity. So once you know all these three parameters, you can very much calculate the pump power that is required to ensure flow. Okay. And I also mentioned how the velocity profile near the wall has a close tie-up. What is velocity profile? The change in velocity. Okay. So between adjacent layers, what is the change in velocity? And that, in a way, talks about the wall shear, because there is something that's holding back my flow. Okay. So now you can see that the pressure drop is affected by the friction or wall shear, right? And the wall shear will affect the velocity profile in a way, right? So the importance very much lies in capturing this velocity profile near the wall accurately. So as a CFD person, if you're not able to capture the velocity profile near the wall accurately, the change in velocity near the wall accurately, it is going to give you erroneous results. You will predict the pump power wrong, you will predict the pressure drop wrong, you will predict the wall shear stress wrong. Okay? So that is the significance or the most significant aspect of any CFD modeling, the near wall velocity profile capturing. Okay. All right. So now coming back to what we were talking about, which is the entrance length and the fully developed region. Now you can see how important it is that the entrance region is properly modeled for conditions of your interest. Okay. What do I mean by this? If my flow is, so let me put out this question here for you. Would you, if I want to cause a lot of heat transfer per se, okay, would you want to operate in the entrance length region, or would you want to operate in the fully developed region? Anybody? Anybody wants to have a go at it? If I want to have large amount of heat transfer, would I want to operate in the fully developed region, or would I want to operate in the entrance region? Do you vaguely remember the Nusselt number plot with?
So they've been answering online as entrance region.
Okay, that's great. So the reason is, all of you might remember this plot quite accurately, which is the Nusselt number plot drops off and becomes constant at some point, correct? So we can see that the entrance region is preferred, right? There are several associated reasons for that, and the main part is that your thermal boundary layer temperature difference is quite large. The profile of your velocity, the transport, is quite steep. There's a lot more gradients that's involved, so on and so forth. So the idea here is to say that in some cases, industries prefer to operate in the entrance length region, which means you have to prolong the entrance length behavior in some cases. So in such scenarios, you as a CFD personnel will be asked to simulate this entrance length region where your velocity profile differs. In some cases, the pipes are so long that you would reach a fully developed profile region, and really your interest is only in the fully developed region. So then as a CFD professional, there is no need for you to simulate the entrance length region, and you only have to simulate the fully developed region. If that were to be your case, you are actually wasting your time if you're going to give a constant inlet and simulate all the entrance length and then come to the fully developed region. The reason is, fully developed region for laminar, if it's a laminar thing, is a parabolic profile. So you can at the inlet itself provide a fully developed profile and monitor any kind of heat transfer or mass transfer, whatever that's going to happen down the tube. So the takeaway from here are two things. Number one is that your pressure drop, wall shear, and your velocity profile are the key things that you would have to monitor. They're very much interlinked to the performance. And singularly most important is that you be able to capture this velocity profile near the wall. Okay? And this velocity profile, if you have to capture, you need to pay attention to the region that you will be simulating. Is it the entrance region that I want to focus on? Is it the fully developed region I want to focus on? What does that imply on my mesh size? How long is my entrance length region? Is it long enough to be important? So on and so forth. Okay. Now, I have mentioned a critical thing here about mesh size and how it is important to capture this velocity profile a little bit more accurately. So I'll just skip this slide and I will come to this part here, okay? Because I think what is important for us to understand is that this near wall cell becomes a very, very crucial role player in understanding how this velocity profile changes. Okay. Now, this is very important in the case of turbulent flow. So let me stop here and ask one question. What do you mean by laminar flow and what do you mean by turbulent flow? What is the meaning of this? It's a very commonly used term, but what do you mean by this? Anybody?
In the layman's word, it can be said that the turbulent flow is one which the fluid particles move zigzag without any, with no control. Like it will not be in an arranged layer by layer manner.
Mm-hmm. Okay, that's go ahead.
And the heat transfer will be better in turbulent flow because chances of transfer is more in such case, especially the convective transfer.
Okay. So to quote what you are saying that turbulence flow is where particles move in a random manner, which tend to get a lot more mixed and hence enhances your heat transfer, right? So let us think of it in CFD perspective, what this implies, right? So if you have a wall, your laminar flow typically implies that your particles are going to be moving in layers which do not mix, okay? So this is going to be your laminar flow profile, which do not mix a lot. Whereas as far as turbulence is concerned, if you're going to look at turbulence, there'll be a lot of mixing or eddies, what they call as eddies, small circular fluxes of velocity that's happening. Okay, so the phenomenon has been observed experimentally to contain a lot of rotating vortical-like structures or eddies in turbulent flow. Okay, this is the basic physical observation as far as experiments are concerned. But as a CFD professional, right, now the question lies as to how am I going to capture this variation in velocity? This variation in velocity for such a complex eddy-like circulating structure, right? What is my velocity, say, at this location, right? What is my velocity at this location from the wall? How do I track what the velocity will be for a turbulent flow? Becomes a question. And unless you do you do not, I mean, unless you try and predict this in an accurate fashion, you will not be able to, like I mentioned, predict the wall shear and the pressure drop accurately. Okay. The second problem is how small are these vortices, and at what distance from the wall, what is the strength of these vortices? What is the velocity like induced by these vortices? Why is this important? If I have a mesh which is, say, 1 meter, I'm exaggerating, the cell center is 1 meter long, we should realize that our equation for momentum is probably being solved here if it's co-located, staggered. I'm not going to get into that. But you're basically going to solve the first Navier-Stokes equation only at the first cell center. So there is a huge unknown gap if I take 1 meter long from a no-slip boundary condition to that cell center value. Okay, so I have no understanding of how this velocity can change. Will it be linear? Will it be parabolic? Or will it have flow reversal? Is that possible? So we have no understanding of this. Okay. Now, then the question is, do I then make a mesh size so small that, I think I have a figure of that here very quickly. Or do I have to make a very small size mesh so that I track every little flux that's happening? The downside of this is your eddies vary in scale to a large extent, right from very, very small eddies to large vertical structures the size of your pipe. Okay. So if you're going to try and capture these small eddies, what you end up doing is getting a very, 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 very refined mesh, which will stop you from trying to simulate this in a timely manner. Okay, it's not practical. You're going into a DNS simulation, direct numerical simulation. So a large amount of us do what is called a larger sized mesh. Okay. And what we do here is we use something called the wall function, meaning empirical formula, if you might say, which will give you at a particular distance y, whatever your first cell distance is, it will give you the velocity at that distance. What it will do is it will presume a profile. It will give you an empirical formula. You can assume it to be some profile. It could be 4.56 ln y plus 3.25, some formulation which gives you the velocity at that distance from the wall. Okay. And most of your standard CFD codes use these wall functions, basically velocity value empirical formulations. I'm using empirical so that you can understand it. There are different ways in which you can solve one equation model. I won't get into that right now. But the bottom underlying idea is you try and get a velocity at a particular distance from the wall. Okay. And that's through something called the wall function approach. So what is the wall function approach? Very quickly to tell you what the wall function approach does is, like I said, at a particular distance from the wall. So it says, based on observations from experiment, the wall function approach typically has observed 3 layers or different trends in the velocity behavior. Okay, right near the wall. Okay, y is equal to 0 to say y plus is equal to 5. I will explain what this y plus is in just a bit. Think of it as a distance for the time being. So right near the wall, it observes that the behavior is almost laminar. So this first layer is called the viscous sub layer or the laminar sub layer. essentially you're saying right near the wall, the fluctuations are not a lot and the flow is almost laminar. Okay. And they did some experiments and came up with the fact that U plus is equal to Y plus. U plus and Y plus are non-dimensional versions of the velocity and distance. So you might ask me, why is there a need for a non-dimensional velocity and distance? So if I were to be doing an experiment with, say, a pipe which is 10 meters long, or even just a flat plate which is 10 meters long, and trying to understand how the velocity varies for that. For, say, a velocity of main bulk velocity, I have a huge 5 meters per second fluid flowing, and I have a 10-meter long tube. Okay. My need is to be able to predict this profile. Now, if, say, Divyesh or Ashley take up another surface, which is, say, 2 centimeters long, okay, and their velocity is 0.1 centimeters per second. Now, they will also have to come up with a velocity profile, right? So typically, you want the system or you want a formulation which is not restricted to the dimensions of the system, but given some values, can I non-dimensionalize it in terms of U plus and Y plus so that it's universally applicable everywhere, okay? So coming back to this, through experiments, it was identified that there are typically 3 regions or changes through which the velocity profile happens. One is the viscous sublayer. The middle layer is more or less a transition layer or a buffer layer to a fully turbulent log-law layer, okay? So, and in each of these domains, they found a different variation for U plus versus Y plus, okay? So typically the log-law layer starts at about 50 or 30 or 50. And between that is called the buffer. Buffer is a region where, you know, the behavior is not really known. The experiment is showing you this value, but the 2 lines intersect somewhere here. So that's like a transition region. And an important advice for you is never locate a cell, which is your first mesh center, in the buffer layer. Never locate it in the buffer layer. Either you resolve it to the viscous sublayer or you put it in the fully turbulent region. Okay. The reason is you might have blended wall functions which can handle all the 3, but errors are more if you locate your cell centers in the buffer layer. Okay. Because you can see the experiment deviates from what the empirical formulas suggest. Okay. So we have understood that for importance or good predictions, you need to capture the velocity profile at the wall accurately. This is more so difficult in a turbulence case because there's a lot of circulations involved and the velocity profile has 3 regions through which it transitions. So it's important to decide whether you want a mesh which is so big that the cell center is somewhere in the 3rd region. So it has to be much bigger for it to be located in the 3rd region. Or you resolve it to the viscous sublayer region. So this is the most critical point that you'll have to understand. So let's, because I want to tie it into the open form part of it. I mentioned something that your velocity that you see in maybe the experiment that I am running and the experiment that Ashley or Divyesh are running, there needs to be a non-dimensionalized version. Okay? So then I have to make these velocity and distance something that can be non-dimensionalized. So you have a U tau and a Y tau, which is used to non-dimensionalize the velocity and the distance. So somebody has to come up with what this parameter is, correct? So in CFD, the U tau, okay. So what did we say? I mentioned to you that near the wall, there is going to be some kind of friction, which is going to slow down or create a wall shear, right? So the wall shear, so somebody took the wall shear formulation. The units is meter square. So the idea here is, can I get something which is responsible for this shear, right? So they proposed this formulation, which is nothing but rho u tau times u tau. Okay, so this is kind of like a flux times the velocity. So you have a formulation which is not exactly, so if you can see, I have put off the order of. Okay, so it is really the convective component which is causing that movement next to the layer of fluid, right? So there's a solid layer and there's movement here. So the wall shear depends on this movement. Okay, so I'm just sitting here and I thought of a formulation which is also convective in form, but I'm calling it a velocity called u tau. Okay, so this is actually something that you are coining. There is actually nothing called a frictional velocity. It is just a term that you have come up with to non-dimensionalize. Okay, so what are you trying to say? You're saying that, okay, I need to have a velocity and I need to non-dimensionalize it, which is here. How do I non-dimensionalize the velocity that I am seeing in my domain? So you say, okay, every domain has a wall shear. So let me non-dimensionalize it with the velocity of, call it the friction velocity, the velocity right at the wall, which is giving me that wall shear. Okay. So this u tau is called the friction velocity, which is a hypothetical velocity which you have come up with, and you formulate it as tau wall by rho, wall shear by the density, using this same units formula. Okay. For the distance now, we will say that my kinematic viscosity, which is basically the property of the fluid. Why do you have friction? It's friction between the layers, right? So you have viscosity, which is contributing, and you're just saying that for units sake, viscosity by this velocity, this near wall velocity, will give me the distance scale, the length scale of this viscosity, this eddy, if you might say it to be an eddy, right? So you have two scales, which is the length scale and the velocity scale, with which you will non-dimensionalize. Say if I'm doing an experiment, I will have to use these two values to non-dimensionalize my velocity that I'm reading. Okay. So in CFD also, it's the same thing. You will have to come up with values of this to calculate U plus and Y plus. Okay. We are to an extent clear till this point. Okay. Because now we're going to make a small jump in all that we have learned, and we're going to make a connect of all that. So let me just see if I can bring that up. Yeah. So right now, I've learned certain things. So let me just put that together. That will help me in CFD. So I have a domain. Right now I have a pipe. Okay. And the first job that you do is I have to come up with a mesh, correct? So I have to come up with some mesh to do it. Now, if I have to decide upon a mesh, then I have to give the first cell center value. I need to give this value. Okay. So then I need to decide what this Y should be. Where is it that I have to solve my first fluid equation? Is my flow very fast that I need to locate the first cell center closer to the wall? That's a question I need to ask. Okay. So then I have to say, okay, what is my velocity near the wall going to be? Is it going to be large or small? Is it turbulent or not? Right? So I need to decide on something. Okay. And what did I tell you? Experiments have given you this velocity profile, which is U plus versus Y plus for a turbulent flow simulation. So then it becomes important that I decide on a Y plus based on an estimation of a rough estimate. I don't have to be very accurate. I think about it and I say, okay, the flow is going to be turbulent based on the Reynolds number. So what did I tell you? Y plus greater than 30. All my turbulence models have a empirical expression which will give me good results for Y plus greater than 30. So I know roughly based on the Reynolds number, my flow is turbulent. So then I need to maintain at least Y plus equal to 30. At least Y plus equal to 30 or more, depending on what computational facility you have. Okay. So if I have a Y plus equal to 30, okay, then what happens? I know my Y plus, okay. If I know my Y tau, okay, I need Y plus equal to 30 because I know flow is turbulent in my regime. I'm just trying to decide what this YC has to be. That is this, correct? So I know Y plus I need at least 30. I do know I have to calculate my Y tau so that knowing these two parameters, I can decide my first cell center size, my mesh size. Then I can go ahead and quickly mesh. Okay. So now I need this U tau, correct? So what did we talk about U tau? Y tau. Y tau is kinematic viscosity, which we do know for the fluid, plus divided by the frictional velocity, U tau. Now, what was U tau? If you remember, I'll just carry this to the numerator. That's what's here. And you know U tau is tau wall by rho. Are we all okay till this point? What are we looking at? We need to capture the velocity accurately. That means I need to decide, first thing I have to do is decide upon a mesh. I have to decide upon YC. So to decide upon YC, what do? I say I know my flow is turbulent. So I should at least have a Y plus of 30, which is the recommendations of several turbulence models. So if I need a Y plus of 30, I have to calculate what is Y tau to get my first cell value. And my Y tau is in terms of kinematic viscosity and U tau, which is nothing but tau wall by rho. Now look at this red circled thing, right? Of all the parameters, I know my Y plus have to be 30. I know my kinematic viscosity. I know my density. I do not know the Y. I want to know the Y, the first cell center, what is the mesh size. And I do not know my wall shear stress. I need to calculate it. So how am I going to do that? Okay. Let's not get into too many details. Typically, what is done is there are standardized experimental values, which will give you tau wall as some function of Reynolds number. If you look up any textbook, it will give you this expression. So what typically people do before they start meshing is, for internal flow, there's a standard expression. They will know the Reynolds number in their system. So they will put that Reynolds number in, get this tau wall. They will plug it in here. So you know everything except the Y. So it will give you a rough estimate of this first cell center, okay, with which people will mesh their domain. Is your job over after that? No. Why? Because you've taken a empirical formula to estimate, some general empirical formula. It might not apply to your system. So what you have to do is, you have to create this mesh, give a simulation, okay? And CFD has the ability, the code has the ability to internally calculate tau wall. How? It will say, okay, my wall is here. I'm getting a particular velocity difference in my first cell. So tau wall is mu du by dy, very simplistically, okay? There are some more complex versions of it. We won't get into that. But it will itself, for every wall cell, calculate the tau wall. Okay, and using that calculate the y plus. It's internal y plus. Okay, you have to print that y plus. Okay, now you have to check if this y plus is 30 or more. Why? Because you started with an assumption that you want 30 or any other value, and you used an empirical formula to decide on a mesh. You have to, during the code, print out the internally calculated y plus and see if it is in and around what you wanted it to be when you started. That is the first round check. Why is this check very important? Because what it means is you estimated that a particular u plus has to be used by the code in the first cell center. That means your y plus estimation should be right. By doing this cross check, you're just ensuring that the y plus that you thought is actually being replicated, and hence the velocity also is accurately being used by your turbulence model. If there is a difference in the value of the y plus that the code calculates and what you calculate, you have to find a midway, keep refining the mesh or expanding it, trial and error till both match. Okay, this is just a first very simplistic check that you have to do to be able to check if your turbulence model is actually what is necessary. Okay, all of this appears complex, but with time you will get used to it. How does this talk connect to the rest of the day? Now you will start off with a laminar flow through a tube, wherein you will look at the velocity profile that's being generated at the outlet, which is a standard fully developed parabolic profile. Okay. From that point on, I want you to try and understand how the velocity has changed right from the inlet to the outlet. Okay. After that, you would start doing the turbulence flow through a pipe, and you would have some reading material on the y plus, right? You would be giving a certain mesh size. If possible, I want you to go back home and do this quick check whether the y plus, which I'm not too sure if we can always probably help you out in that. You can also Google how you can print out the y plus, but I think typically the code does give out the y plus as it's printing that solution. Okay, so it's just a first round of trial to understand how critical this y plus value is to the accuracy of your result. So from laminar, you move on to turbulence, and you will see how the velocity profile has changed because it's turbulent flow. And the importance of y plus has been discussed here, which you can use to check the efficacy, the accuracy of your simulation. Okay, so we'll stop at this point, and if you have any quick questions that I can take before we go to your laminar flow through a tube tutorial.
Ma'am?
Yeah.
Ma'am, in a couple of minutes ago, you mentioned about y plus being calculated from the wall shear stress. So over there, actually, that relation is used to calculate y, no, ma'am. So y plus, you had experimentally concluded that it is around 30 for the turbulence models. So I don't understand y plus calculation from tau w.
Okay. There are certain layers which we'll have to get into. Let me just try and see if I have it here. Okay, let me just go here. This is going to be a huge jump. Okay, to prevent the lecture going into several. So let us understand, or let me go to a fresh page and draw it. So first question here is, you would know the bulk velocity of your flow, correct? A typical rough bulk velocity. So you will know your Reynolds number, and you will know it to be turbulent or not. then you will have a first round choice of what turbulence model you want to take. Okay, so let us say you want to try K epsilon. Okay, and this model will come with a recommendation of what Y plus it can handle. So from 50 to say 500. What does it mean? It just means that it has this expression for velocity U plus versus Y plus. That's what it will know. Okay. So now this means that if you want to use a K epsilon model, which is your choice, you know roughly the Reynolds number to be turbulent, right? So you need to then decide where you want your Y plus to be. It has to be between 5 and 500, 50 and 500. Okay. So I don't want to go to 500, but if I want to remain in and around 50, 200, this is based on your computational capabilities. Say I choose a Y plus to be 50, the finest mesh that is possible for this model. Okay. So now I have to decide on, these are all just pen and paper work. Now I have to actually mesh, right? So if I have to mesh, then I need a first estimate of what the cell size has to be, the first cell size. So then I do have to, based on my decision, try and decide what Y I have to give. So I do know Y plus is equal to Y by Y tau. I do know this. So if I need a Y plus of 50, I need to figure out what Y tau is so that I can get a Y. Now, for this Y tau, then I need to go back to nu by U tau. Okay. And if I do need a U tau, I do know nu by square root of tau wall by rho. Now we have come to the tau wall. This is still pen and paper work, and you need a tau wall. So you're going to go into literature for a generic tau wall empirical expression, which will be some function of Re, some numbers like 4.65 Re per 0.8, something like this. Okay. So you do know the Reynolds number in your case, a rough Reynolds number in your case, bulk Reynolds number, and this is an experimentally obtained expression for bulk Reynolds number. So you will plug that in here and get a tau wall. So once you've got a rough tau wall, you plug that in here, you know your kinematic viscosity, you know the density, you know tau wall. So what do you know? You know U tau. Okay. You said I'm going to use K epsilon, which is I need a rough thing of 50. So I know a Y plus, I now know a Y tau, so I can calculate the Y. So for my first step to mesh with just pen and paper, I do have an estimation of my first mesh size that I have to do. Okay, just pen and paper, and it all hinges on what? This particular empirical expression of tau wall that you have taken. Okay, but that is generic for a very, very standard case. Okay, now say you go into your CFD simulation, you created your mesh, and the solver is going to solve. Okay, internally, the solver is going to do conservation of mass, momentum, and energy, fluxes, so on and so forth, right? Across all the cells. And it comes up with a localized velocity at every cell center, correct? So now it has to come up with, now can I calculate, after I did the simulation which has small meshes, can I then, I know the velocity here, I know the velocity here to be 0, okay? Can I, because I know wall shear is equal to mu du by dy. There is going to be a turbulent component to this, but I'm not getting into that. So if I can calculate du by dy, I know y, what is the distance? Delta y I know. Delta u I know, un, that center velocity. So for every cell, I will have a localized tau wall, correct? So if I have a localized tau wall, can I calculate y plus? I do know my cell center. I do know my tau wall, which is local. I do know my viscosity rho. So I will get a y plus, correct? Now the question is, the localized tau that you calculated and the y plus you got, does it match this generic version or not? If it doesn't, you will have to change your mesh size so that there is some consonance between what you're assuming and what the code is obtaining. Why is it important? Because the code sees one particular y plus and it will go take that particular velocity, right? Whereas you are estimating a y plus and you're saying, I need that particular velocity. So you're trying to mix and match so that there is a adherence, trial and error, at least in the range. It doesn't have to be exactly one on top of the other. Does that make sense?
Yes, ma'am. Got it, ma'am. Thank you.
Yeah. So I think, Shweta, do you want to start your tutorial?
Yeah, I think that was a great session. Thank you, Professor Janani.